Hello, my name is Alexey Dobrovolsky. I am from SPH Engineering. Today we will discuss two big topics. First topic is how to plan drone missions with SENSYS MagDrone R3 and Rfo magnetometers. Second part is how to process gathered data in Oasis Montage. In my part, we will review R3 and Rfo magnetometer systems in regards of mission planning. I will demonstrate how to plan the mission in UgCS ground control software and how to import data into Oasis Montage. Victor will demonstrate workflow of data processing, with most interesting part how to estimate the depth of detected objects. R3 and Rfo systems, magnetometer systems, have absolutely the same sensors, but R3 magnetometer has two sensors, here and here. Rfo has 5 sensors distributed along 2 meters long bar. That's the main difference. Both systems has very simple, similar components: magnetometer with sensors, data logger of magnetometer, UgCS SkyHub onboard computer, and radar altimeter here. Rfo, almost the same: magnetometer with 5 sensors, data logger is here, radar altimeter, and SkyHub. Both systems can be used with many types of commercial drones. Here is DJI M300 RTK. For both variants, we use UgCS ground control software to plan missions and to execute the flights. What is SkyHub and its role when we are doing magnetic surveys with R3 and Rfo systems? Actually, SkyHub is on-board Linux-based computer. It is compatible with almost any commercially available drones. And its role when we use it with DJI drones is to manage the flight in true terrain following mode using real-time data from radar altimeter. For magnetic surveys, when we need to detect small artificial objects like utilities or unexploded ordnance, it is very important to fly as low as possible. All samples of test data what we can provide gathered from altitude 1 meter, and for such low-level flights it is absolutely necessary to have the system which will allow the drone to keep more or less the same very low elevation above the ground. Additional function of SkyHub is to provide GPS coordinates stream into data logger of magnetometer. DJI M300 has RTK receiver on board, and if drone is flying in RTK mode, we can stream very precise coordinates directly into data logger, and we will have precisely geotagged data right after the flight. And also additional useful option of SkyHub is support for forward-looking radar sensor to detect obstacles in front of the drone. It is very important for low-level flights when usually our survey area can be surrounded or can have inside of survey area some obstacles like fences or bushes or something. That option can save your drone. So, mission planning. First of all, we need to know, of course, area of interest. Customer of the survey can provide that area in the form of KML or KMZ file prepared in Google Earth or in any CAD software or mapping software. UgCS can import such file, and we can use it as a base for our planning. Also, it is very important to have a fresh map, high resolution map, to avoid obstacles like fences or bushes at the stage of mission planning. So resolution of such map data should be enough to see such small obstacles, and usually we recommend at the first stage of surveys to do a preliminary survey using photogrammetry to generate fresh orthophoto map. UgCS can import such maps. Next important things we will discuss. First is how to select distance between flight lines for R3 and Rfo magnetometers. For R3, we have two sensors. The distance between sensors is 1 meter. So if we want to have the same distance between lines for every sensor, for magnetic sensors, we may select 2 meters distance between flight lines. So we will have equal distance between lines for magnetic sensors. If we want to collect data with higher resolution, half of meter, we will need to use half of meter distance between flight lines. In case of Rfo magnetometer, here we have 5 sensors. Distance between sensors is half of meter. And to have the same equal distance for the sensor lines, we need to select 2.5 meter distance between flight lines. And we will have a very high resolution of the gathered data without gaps between lines. You can see that difference is huge actually. If you want to collect data with same resolution, if we use R3, we will have to select distance between flight lines just half of meter. Here 2.5 meters. Flight time of the drone with R3 and R4 more or less the same, maybe 35 minutes for R3, 30 minutes for R4. So you can see that performance of productivity of field work when we use R4 and collecting high resolution data at least few times higher. Next important topic is flight altitude, actually balance between flight altitude and speed. Remember that amplitude of magnetic anomaly will decrease as third power of the distance between object and our sensor. So that means that every time when we are searching for small artificial objects, we have to fly as low as possible. Of course, we need to take in consideration additional aspects like wind and slope in our survey area. You see that R4 uses a long bar, 2 meters, and it is not recommended to fly with R4 if we have side wind at the moment of our survey at very low altitude, because in turns or in case of wind gusts, end of our long sensor bar can touch the ground when drone will try to compensate side wind. Also, very important to know that terrain following algorithm has approximately half of second delay. We can make it much more quick, but in such case, if we will react at every even small change in elevation, our data will have a a lot of low frequency noise which can hide real anomalies or generate host anomalies in our magnetic data. So algorithm has delay, and what we will get. Here at the sketch you can see some ground surface and ideal trajectory of the flight, which is strictly parallel to the ground surface, but in reality, because of delay in algorithm, real trajectory will be shifted. That means, for example, if we are flying at the speed 1 meter at altitude 1 meter above the ground, and we have slopes 45 degrees in our survey area, our drone can touch the ground because of delay in algorithm. So solution here is to increase the altitude or decrease the speed or fly parallel to the slope. I mean not up and down on every flight lines, but fly at the lines which will be approximately at the same absolute altitude. Speed we need to select based on safety considerations only, because R3 and Rfo magnetometers have a very high sampling rate, 200 Hz, and we need to select our speed. We need to select our speed based on the balance between altitude, how rough is our terrain, and our experience actually. So our general recommendation, when we are flying at the altitude half of meter or up to 1 meter, we need to select the speed 1 meter per second. If we are flying higher, we can select higher speed. Good thing here that even if we use too high speed or too low altitude, cost of the crash will not be very high because of very low altitude of the flight. In most cases, you will need to replace only propellers. I will demonstrate how to plan the mission in UgCS. That lovely place is Office of SENSYS, manufacturer of magnetometers, and here is test range with a lot of disarmed unexploded ordnance. First, I will create new route, R3 test flight, select DJI M300 drone, and first I need to set first waypoint and set our survey area. UgCS will calculate the route, and we need to set here flight parameters. First, sight distance. If we use Rfo, we will usually set 2.5 meters between flight lines. And we need to set direction angle. Usually it should be parallel to the main axis of our survey area to minimize flight time and number of turns. So here I will set 270 degrees. So route is calculated, and actually we can flight it. Important note that if we use drone equipped with true terrain following system with altimeter, radar or laser altimeter, flight altitude what we set here at the planning stage will be ignored, and we will set it at the flight time. just before our flight. So route is ready, and my last topic today is how to import R3 or Rfo data into Montage. Data during the flight, data is logged in R3 or Rfo data recorder, and after the flight we can connect to data logger using USB cable and download binary file with magnetic data to our laptop and to export data into CSV format, which can be imported into Montage. We can use software called SENSYS MagDrone data tool, which comes with equipment. I will open the file from Magnetometer. We can see here trajectory of the flight, and first step is to detect separate tracks. Detect. We can see that flight lines are detected, and we may now export data. We can export raw data, but we also can export pre-processed data. ASC files actually are also CSV, but after some processing. In most cases, we will use ASC files, pre-processed files, because data tool has standard filters or processing steps, which are very useful and can minimize amount of work when we will deal with data in Montage. Data tool has low pass filter and compensation algorithm to compensate movements of the drone in magnetic data. In most cases, we can use parameters of the filters and algorithms by default, and we can check what we'll have after export. I will use data downsampling to minimize export time. We can see preview, but also with the detected targets we can see one issue. Issue is you can see it here. We need to compensate a GNSS time lag in our data. I know that for that flight time lag is minus 400 milliseconds. Two main sources of time lag is a physical distance between GNSS receiver antenna and our magnetometer on the drone. Second is delay in software, and that time offset usually is systematic for fixed system. So now I will specify minus 400 milliseconds and will repeat the export now without downsampling. Okay, and we see excellent results here. So, what we have in the data? In the data, in exported data, we have some timestamp, we have sensor ID. In Rfo Data, we have sensor IDs from 1 to 5. We have coordinates for every sensor, and we have calculated total field anomaly. Remember that I used standard data processing algorithms in data tool. So data is cleaned using low pass filter to eliminate high frequency noise from the drone, and also data is compensated. But here we also have for every sensors XYZ components of magnetic fields, and Z components are not filtered, not compensated. So if you want to deal with raw data, you can still do that in Montage. And final step is import into Oasis Montage. I will create new project. First I will create new database, Rfo Data, and click database, import text file. Here I need to select database, I need to select file with our data, and I need to select import template. Actually, it is mapping between fields in input data and columns in Oasis Montage database. And click OK. Data is here, and we can see that we have absolutely the same as in text file. Final step is to set projected coordinate system. Source data is in UgCS 84. And we want to use UTM coordinates when we will process the data. I know that UTM zone for Census test range is UTM 33 north. And now we have UTM coordinates in our data. That's all from me. You can find additional resources about magnetic surveys planning, especially for low altitude flights, and you can find my paper published in First Break magazine, how to use elevation data, how to use photogrammetry maps when you plan your flights. Victor, floor is yours. Thank you.
Oh, thank you, Alexi, for your presentation. That was good and very informative. And I would like to say good morning, good afternoon, good evening from everyone who is joining us from wherever you are all across the world. And my name is Victor, and I'll be walking you through how you process this data that is acquired from a Macdrone R3 inside of Oasis Montage with these targets that we have plotted them inside Oasis Montage, as you can see in front of my screen. So this is the data that we have, and the first thing that we need to do is to plot the lines after we have imported the data inside of Oasis Montage. And you can see the data right now, which is plotted on your screen. And when you zoom in, you can see the lines have not yet been split. And that's the first thing that we are going to do. So for us to do that, the easiest way would be for you to go to Database Tools and then go to Channel Tools, and then we need to make what we call a distance channel. This is simple calculating the distance between each individual sample that is measured, and then you add them together to get a total along the line. And the name of this channel will be called distance. What you need is to have your X and your Y channel indicated, and you would have converted these to UTM. And then you just hit the OK button. And then you get this distance channel that is created. So the length of the line in total is about 4 kilometers. And this is what we are going to be splitting. And then what we are going to do next, you go to Database Tools, and then you go to Channel Math. And then with a simple expression, you need to calculate what we call sample separation, which is what is the distance between each individual sample that was measured. So the way we do that, we use a simple equation, which is C0 is equal to C1 minus open bracket C1 dot offset open bracket minus 1, and then you close bracket. C0 is equal to C1, right? So C0 is the new channel that's going to be created called the sample separation channel. And then C1 is your distance channel. And then you just hit the OK button. Right? Now we have this new sample separation channel. I'm just going to increase the number of decimal places so we can see what's happening. Let's make it 5 perhaps. Right? And then we're going to make a profile of this sample separation channel by going to sample separation, and you hit the show profile button. Right. So what we can see here is that we have a sample approximately every 0.0042 meters or 4 millimeters. There's a sample that is measured, and then you can see that as a constant value that you see at the bottom here. That is the 4 millimeters. That is constant, but every now and again you get a peak. So for us to have a closer look at that, I'm going to put my map together with my database side by side. If you go window and you say tile vertically, let's close this one. Right. And then we want to have a closer look at what is happening here. So you can link your map and your database. And to do that, you click where it says pen to cursor on all maps. And then you click as well the data linking tool on your map, so that what you do on your database is also linked to your map. So where you move, that is also where your database and your map will also move. Now they are interlinked. Right. So let's start at this point. So this is the start of the line. You can see as I move, you can see my map also starts to move on the right. So at every point here, we're still at 4 millimeters, which is the constant value that you get here. And then at around this peak, let's zoom into the peak. When we are at the peak here, that is the point where there is a 10, and the value at this peak value, it sort of peaks, and it's slightly higher than the 4 millimeters. You can see we have a value of 76 meters, which is the distance between the one point to the next, right? We also have, if you look closely, there's this smaller peaks that you see here that I'm going to zoom into, right? So this is us just inspecting our data before making a decision on what to do, right? And then let's see what is this value here. It's 0.05, which is quite consistent. It's fine. And then keep going, just keep going. We're still good. Watch where the map, what is happening on the map on the right. We want to see the difference between the samples. We're still at a distance of 5 millimeters there. This is what we are interested in. This is the point where it changes from 5 millimeters and goes to 0.9 meters. So this is what we're going to use as a guide to split. You can see the other one is 70, and then this smaller one is about 0.9 meters. So to split these two, you go to database tools, right? And you go to line tools, and then we're going to split on XY breaks. So we're splitting for our lines in any direction, right? And then we're interested in this downline distance. We saw that we have at the downline distance, basically what it is telling us, it refers to the general direction of the line. And the value that we input as the downline difference tolerance is what is going to be used to split the line when two consecutive points along an input line are further apart than what we are calling our downline distance. So we had a value of 0.7 meters. So we're going to say if the downline distance is 0.6 meters between two samples, then we want a split along that place, right? And then we're going to say we're going to split all lines, right? And we want the new lines to be sequential. We want to maintain our line type. The first line we want to be line 1, and the rest of the lines and the line increment of 1 as well. So the first line will be line 1, the next line will be line 2, and then we're going to reset to fiducial start to a value of 0. And then we're going to click OK. There you go. So let's have a look at this. Now the lines have been split, and if you list them, you can see we have line 1, line 2, line 3, right up to line 30. I'm going to replot this just to show what we have done. So to plot the lines, you go to map tools, line path, and then we're going to make it, perhaps let's make it red so that it is different from the lines that we had previously, right? The line path already exists, and when we're going to override it, click yes. And then we go into our map, and then you can see our lines have been now split, starting with line 1, going all the way down up to line 30. So that's just how easy it is to split the lines when that you have imported from your SENSYS MagDrone R3. Okay, you can see, can just also cross-check what you have on the right. The lines have also been split this side, and we are done with the splitting of lines. Okay, so let's go back to our database and have a look at that. We don't need this sample separation for now. We can delete that. And so the Macdrone has got 5 sensors, And you can see with the separation, there's a separation. So line 1 is only made up of sensor 1. You scroll down, sensor 2, sensor 3, sensor 4, sensor 5. And the distance between each sensor in this case is 0.5 meters. And you could have also checked that if it is correct from your map. If you look at the bottom, keep your eye at the bottom right hand of my screen. If you right click, say measure distance, and you can measure the distance between each individual line, which is, as you can see at the bottom right of your screens right now, you should see that as 0.5 meters, right? So the next thing is for us to inspect our data. We have a total field anomaly. If I right click, let's say show profile. This is our magnetic data, right? And then these are the mag X, mag Y, and mag Z are the individual components that were measured. If we look closely at the data, it looks to be good data, right? But someone, let's say, rescale all, looks to be quite good. In some places, it looks to be quite noisy as well. You can see this high frequency noise that we have. And therefore, one might want to perhaps apply a low pass filter here to remove some of this noise. All right. And that's the next thing that we're going to do to sort this out. So there are a number of filters that we can use inside of Oasis Montage. You can find some of them if you go to database tools, filters. We have quite a few filters that you find along this menu here, right? So in our case, we want to apply a low pass filter to remove the high frequency noise that we are seeing inside of our data, as you can see right there, right? I've already done that, and I'm going to just plot that as well on our screen so we can see what it looks like, and we can be able to kind of compare what we have and the filtered data. And you can see the filter has sort of done a decent job in trying to remove the high frequency noise, right? So this is now the filtered data that we now have. Then I'm now going to load our UXO menu, right? I'm going to load it right here. So what we are going to do next is to calculate the analytic signal. So to calculate the analytic signal, we need to go into the UXO Marine menu, and we're going to be calculating step by step from the total field. And you can see what we need there. It's a 4-step process. You need to create the total field, calculate your derivative grids, smooth them, and then you can always display and calculate the analytic signal after that. But before we go into that, let's just explain what the analytic signal is all about. So if you are moving from your total magnetic field intensity to your analytic signal, to get to the analytic signal, as I have shown from the 4-step process, you need to calculate your derivative grids in the X, the Y, and the Z direction, and then you square them, and then you calculate the square root. By virtue of you squaring them, it means it is a positive value, and it gives you a body-centered anomaly. As you can see, this is what it will do moving from the TMI to the analytic signal, which gives you a much simpler way for depth computation. Okay, so let's go back into the software and see how we calculate the analytic signal. If you go into this menu, you can able to grid the data. I've already done this and I'm going to show you what it looks like. This is the gridded total field data. And you can see these dipole anomalies that we're talking about, where you have a high and a low next to each other. We have a high, a low, a high, and a low. So the analytic signal, what it's going to do when it is applied, it's going to produce this body-centered anomaly that I mentioned earlier. And then what you do next, we go into analytic signal, and then you can calculate the derivative grids for using the total field grid that you would have calculated earlier, and you've got these three resulting derivative grids in the X, the Y, and the Z direction. Okay, so this process of calculating derivative grids will generally result in some level of high frequency noise, and that high frequency noise may potentially lead to spurious depth estimate, and we need to remove this noise, and we do this in the next step. Okay, when we go analytic signal from total field, and then we need to smooth uh, the derivative grids. So, and this just provides a way for us to filter the derivative grids using a Henning filter prior to calculating the analytic signal. You can do this a number of times. Personally, I'd advise that you do it once or perhaps most 3 times. If you see yourself doing this more than 3 times, you probably need to go back and look at your total field data for any noise that might be leading, that is still, you are still seeing in after running 3 passes of your Henning filter in efforts to remove any high frequency noise that you have in your data. When we've done that, 4th steps, as I said previously, would be for us to calculate the analytic signal, right? So I ran a smooth filter once, right? You can see I've used SM1 to say smooth, and by default it gives us the output as the analytic signal. It calls the output analytic signal as AS. I'm just going to rename this to analytic signal. Okay, and display the grid. Click OK. Onto the current map, some shading as well. Okay, so what we see there is the analytic signal on our map. Let me just change a few things there and change the color distribution from histogram equalization to maybe normal distribution with a standard deviation of 10. This will generally just tighten the smaller anomalies, and you can start to compare and see what you're starting to see now, a more body-centered anomaly after we run that process. You can see there's some noise in the data. There's high frequency noise that you are seeing there, and right. I'm going to play around with the color distribution a little bit more there. Maybe let me change this mean value to 40 and change the standard deviation to 5 and see what that looks like. Okay, that looks much better for me, and I'll accept that. And for what I'm trying to do here, this looks okay. Right. As soon as we've done this, the next step is for us to pick some targets. we're going to use the Blakely method, right? The input grid is our analytic signal grid. The passes of the smoothing filter that we're going to use, I'm going to leave this at 0, right? And what this does is to apply to the grid so that low amplitude, it also removes some high frequency noise. And at this stage, I don't want to remove more data than what I already have. That's why I'm going to leave this at 0. And then for the grid value cutoff, I'm going to use a value of 35. This may be provided for you during a project, right? So if you wanted to find this value, you may calculate a noise envelope if a value has not been provided for you. And to do that, you can go to database new and you create a new database. Let's call it noise envelope. All right. Click OK. And then you can then go to grid image, go to utilities, and then you can go and say grid profile, right? You want to calculate to get sort of a background noise envelope from the analytic signal grid, and you're going to call this a new line name. Let's call it L1 for line 1. The sample interval, I think it was 0.00425, same as the sample interval that we're using. And then you can digitize from your map. Choose the option to digitize from your map, and then it says enter points on profile. Right click button when you're done, and then what you do, you just go avoid any anomalous areas, right? Do this throughout your map. Okay, I did this earlier and I'm going to show you what mine looks like. Let me come out of this. So let's open this noise envelope database that I did. If you right click, you say show profile, you get an idea of what that background noise envelope looks like. Double click twice and right click and say statistics. You see the maximum value there is 32, right? And then you might want to check that that value 32 does not sit very close to an anomaly point of interest that might potentially be a target. I checked mine, so that's why I'm going and I'm choosing to go with a value of 35 in my case. So I go to UxO Marine, Mag, and then I go to pick targets from Grid Blakely, right? Pick my analytic signal. I'm not going to be running any more filters at this stage. Choose a value of 35. We don't have a target database, so I'm going to create a new database called targets, right? And inside this, there's going to be a group of anomalies that are going to be called targets. And the mass channel, call it mask. Grid value channel, we shall call it analytic signal, right? We're going to plot these anomalies, let's say with size 7. They're going to be plotted on my map, and then you just hit the OK button there. And we see what it looks like. Okay, so it doesn't look too bad. If you those are the anomalies, perhaps maybe we should change this to red, another color for better visibility. It's going to make it red, make them slightly bigger as well. Put the size of 30 there. Okay, so these are the anomalies that have been picked. It's an automatic process, but at this stage, it is advisable for you to inspect these anomalies, okay, and decide, do you want to keep all of them? Are you happy with all of them? This is the part where the user needs to make some choices based on their knowledge of the project and make some judgment calls from what they are seeing in their data. Okay, so the targets have been picked up, and we can always open now this targets database there. Just double click on it and you can see we have a target ID channel, and from there we can see we have more or less 65 targets that were picked up, and you'll see that this is the value of the analytic signal of the picks that we have, and all of them should be above 35, which was our minimum cutoff value in our case. So at this stage, you may want to spend some time inspecting your targets to make sure that you are happy with them. You would be advised to probably remove some of these targets that are on the edges, because it would be hard to plot a polygon around them, which is what we want going to be doing in the next step. And just spend some time doing some QC and making some decisions on how you want to treat these individual targets that would have been picked up. Basically, to do that, you can go under Manage Target List, and then you can always choose to move some of the targets and to remove some of these targets. Out of interest's sake, let me just choose one. I'll go with the option to remove targets from the target list, right? The targets that we're working with are the target database. The group is called targets, mask, analytic signal. I'll go with you can either choose to click on an individual target or a polygon. I'll just choose the polygon option. Okay. You see this cluster here, and then I'm going to draw a polygon around this cluster, right? And then right click when I'm done, and then those targets are removed. So these are some of the choices that you would make, and you will see when you're done, you just right click and say done. If you go into your targets database at this stage, you will see that some of these targets that you have removed will have an asterisk, which means that they will not be used for any further processing. The ones with a 1 are the ones that are used. So we do not delete the targets in case you do decide to come and use them, or you change your mind for any other reason, and you can just come and use these targets by entering a 1 into your mask channel. Okay. So the next step for us after we have done this is to go inside the UXO Marine Mag menu. We have picked the targets using the Blakely from grid. So our next step, remember our menus are from top down fashion. That's how the workflow is designed, which makes it quite easy for people to use it. So after we've done this, we're not using the Euler method in this option because we have too many targets that are clustered, as you saw from the map. So we're going to choose to calculate the signal strength and signal to noise ratio and size, right? So what you need is you can either choose to use a database or to use a grid. If you choose the option to use a database, then a grid will be calculated for you. So my recommendation would be for you to rather use a grid, because you have already gridded the data, and when you gridded the data, you had better control of how the data was gridded. And the target database, you pick up your target database, targets, mask, that's your target mask channel, and target ID is the target ID channel, right? And then we're going to use the user defined option. Remember, we used a background of 35, or you can use then a noise level of 4.12, right? If you wanted to, you could choose to say interactive, and then you could use this button here to calculate the background. That is what I did earlier, and that's how I got this value of 4.12. Okay, so, and then our data, since we are working with the analytic signal, we have monopoles, all right? And we're going to create new polygons, and we're going to call them target, and we're going to create them inside. I've created a folder called polygons. You select the folder, and the name we'll call it targets, and then you hit the OK button. All right, just say yes to all, and then new channels are going to be created. We'll just have a look at these channels when they're created. Right. So we have these 4 channels that are created. The first one is signal to noise ratio analytic signal. And then we have another one, signal strength analytic signal. And we also have size analytic signal. And we have the extent flag. The signal to noise ratio analytic signal. What this one is calculated as the sum of the squares of all the points within the window and above that are above the background. And then, so this one, the signal strength channel, this one is calculated this one is the one that is the sum of the squares of all the points within the window and above the background. So that's what we get from that one. And then we also have the target size, which is an area around the polygon, and its units are the units of your map, which in our case is meters. So if it's area, it's square meters. So that's how it's calculated. Okay. So those are some of the channels. If you want to know more, you can always go inside the help file and you scroll to the bottom. We have good notes explaining everything and how the mathematics behind these calculations. But for the sake of time, we are going to skip all that and move on and plot the polygons onto our map. To do that, how we do that is you click and then you go to target maps, and then we click on display target windows, right? And then you choose your options there, the targets database, targets group, target ID, right? And the map to display, we're displaying on an existing map, and the target window is the existing target window. And we just click OK. And then you'll see that it plots polygons around the targets. Let's zoom into one in particular, right? You can see it plots this polygon around the map. So if you are unhappy with any of the polygons, you have the option to redraw them. And you can do that by going, let's say, let's choose this polygon here. Let's say I'm unhappy with this polygon. You just go to UXO Magmarine, right? And you go to target maps and you go to the option that says redefine target windows at the bottom there, right? And the directory should be correct. Let's just select folder. Everything else looks right. Click OK. You get about 24 vertices, right? And it says you have chosen target 55 and click yes to move the vertex. If I click yes, I now have the option to move these vertices around. I can click and move them around to where I want them to be located. So that's how you do that if you want to move any of those vertices. And when you're done, you right click and you say done. Okay. So it's as simple as that. And if you choose to redefine your polygons, then you would have to go back again and recalculate the signal strength and signal to noise ratios again, right? So you would have to recalculate this, but instead of saying create new, we have to say use existing option. That's the option that you would go with. And then finally, the last step that we need to do is to model the depth of the targets using model targets batch option there, right? So at this, you choose the where are your target with the database where your targets are sitting, which is the targets database in my option. Mask channel, remember some of the targets we have chosen not to use them, so the mask channel is quite important as well in this case because it is key in excluding some of the targets that you have decided not to use, right? And the altitude channel, I would encourage you to please spend some time and do your best to make sure that you get your altitude when you're doing a drone survey. Get it right, get those numbers right, and make sure that those numbers are correct because it is very much important in the estimation of depth in your data set. And then the target window size, you can choose a target of interest and measure the distance across the target, and that's how you get that number. In my case, I measured a value of 6. My survey was done in 2021 December the 28th, right? So, and then you click on recalculate, and then it will calculate the total field inclination and declination for you. And then as soon as you're done, hit the OK button and give it some time to run. It will calculate depth for you together with other channels, which are going to be displayed inside your targets database. Let's give it a few seconds and we'll get a result just now. When it's done, there you go. And then you can go inside your, close some things here. I want to display window tile vertical. I want to display my targets map targets. Let's place them like that. And then let's look at the depth channel. This is the depth channel. And then we're going to plot the targets that we already know, and then we just want to compare these together with the targets. Okay, so with the way we do that, if you go to data linking tool, and we're going to use these targets. So if I click into the fit depth, right, let me zoom in there. So my fit, the depth that I calculated is 1.2, and the non-measured depth is 1 meter. It's not too bad. Look at another one. I calculated as 1.5. The actual depth is 1.3. Let's look at perhaps this one. I calculated 0.95 meters. The actual depth is 0.93 meters. So our modeling is not too far off. If you look at the numbers, we're not doing too badly, really. One might consider this to be within acceptable limits. Maybe one last tool that we can show is one tool that was recently added to make it easier to display what is being calculated by target modeling. So we have this new tool here. If you go to UX or Marine Mag, scroll down to create modeling results map. You have these options here, and this allows you essentially to choose the target database in this section, right? And then you can also choose the modeling database at the bottom here, which contains the data that was inside our polygons during the depth modeling. You can display as well the residual field, which is the difference between the observed and modeled results, along with several modeled parameters that you see there. Okay, it takes a while to run this tool, so I've gone and created it some results earlier. You can choose anyone. Let's look at this one, map 11. What you see is the final result right there, the modeled as well as the residual, as well as the parameters that were calculated with this result. Okay, thanks again, ladies and gentlemen, for joining us today. We will answer all the questions that are inside the chat box that people have been sending through. But if you do wish to reach out to us, please feel free to write to us with all your technical questions. Write to support@sequent.com, or you can contact me directly if anything has to do with Oasis Montage and the processing of data, of your magnetic data or your EM data when you are mapping your buried objects. And when it comes to the planning of surveys, write to UgCS@UgCS.com, and our friends there will be able to respond to you with all your questions. Thanks again. You have a wonderful day from wherever you've joined us today. Thank you.